So many students have difficulty with lateral forces initially. I'm providing this video to help you understand the calculation aspect of it. It's rather systematic, but if it's the first time, it may be confusing. So just follow along step by step, and you'll see that it is a very rational process. And most importantly, understand what elements are supporting what other elements and how this idea of continuity of transferring the force from element to element occurs. So we're going to start with looking at a box-like building and just calculating the magnitude of the gravity loads that will, or the dead loads I should say, that in turn are activated by the seismic force and how that translates into a static load that we can then analyze as it propagates through the building. So we'll look at a seismic load example here using this simple box building, 100 feet long by 60 feet wide. It's 20 feet from the foundation up to the roof level and then 2 feet parapet on that. So to begin with, anytime we have a problem that involves lateral forces, we want to divide this into segments of 100 foot or 1 foot wide strips. So I've divided this up into chunks like this, and we analyze just one of those. So in the case of wind load, we would have the entire surface being pressured by that wind. Now this is going to vary as we go in height. I'm just showing these all the same. And there's our 1 foot segment there. So we will extract that 1 foot, and here's the wall. So we see the wall has a support at the base down here because of the foundation. Then we have a support at the roof and our little bit of parapet sticking up on the top. And this becomes a 1 foot wide strip, and the depth is whatever the wall thickness is. And that load is an area load over here in terms of pounds per square feet. This becomes pounds per linear foot because it's a 1 foot wide strip. And that load causes that wall element to span and bend between these supporting points, just as though it were a regular beam. Now, things are slightly different when we talk about seismic loads, only in terms of how the forces are generated. Again, with wind loads, we're talking about a pressure that exists over the entire surface here. Seismic loads are a little different. So I'm going to look at an illustrator model here. Here is our a section through our building. I'm not showing anything on the interior on either of these models. There are likely to be columns and other structural elements that we're not interested in directly for the lateral forces. So with seismic load, basically it's the inertial mass of the structure that's causing the forces to be generated. The ground moves, but the building wants to stay put, just as the same way that when you're in a car and you accelerate, you're pushed back into your seat, or a fast elevator, you can feel pressure on your feet, or you lift up a little bit. And so for our building here, the arrows represent a back and forth cyclic motion of the ground. And so as the ground moves, you see the top of the building kind of wants to stay put there. And so we'll just leave it in a displaced fashion. Okay, this would be similar to a ground movement from the right-hand side of the screen to the left, and that displaces the foundation. So the wall element is spanning across here in the same way that it is for wind. It's attached to the ground here, and it's attached to the roof. So effectively, that wall is leaning on the roof structure. And so that gives us, again, the same kind of behavioral condition here where the wall spans from the foundation to the roof, but what generates it is actually the structural self-weight, a portion of that structural self-weight. So this view now shows a segment. Because we're spanning from the ground up to the roof, essentially half of that load is going down to the foundation, and the other half, plus this little piece, the 2 feet at the top, those are being supported by the top slab. So we can extract that 1/2 because, again, half of that load goes down to the ground, half goes up to the roof. We extract that portion of the wall plus this portion of the wall and a segment of the roof, all of which are 1 foot wide. And we're going to calculate weights of these two wall segments plus the weight of the roof. And a portion of that weight, a certain percentage based on our seismic calculation, will then become a lateral force that exists along the top, just the same way as it is with wind. And that wind load or seismic load gets transferred into the roof diaphragm, or if this is a multi-story structure, this would be the floor plate, and wind load would be generated by half of the load above and half below. For seismic load, we would take the wall segment halfway below and halfway above plus the floor plate. So it's the same calculation, just one additional set of forces. So this causes the diaphragm to bend. The wall, whether it's a shear wall or a braced frame or a rigid frame, that becomes the stabilizing element in the same plane, the same direction as the load is going. And so that's where we go to with our calculations. All right, so here's our building in diagrammatic form. 100 feet long, 60 feet deep, 22 feet tall to the parapet, 20 feet up to the roof line. So again, we are splitting this up into 12-inch segments, both in the north-south direction. North is going up on this page, and also in the east-west direction. So we need to calculate loads in both directions. So a typical section through the building here, section A. This is the C shape that was shown on the computer model. That's the load that we actually want to calculate. The wall effectively is spanning between the roof, which is supported by a horizontal resisting element, a shear wall, a braced frame, or a rigid frame. And so the wall then leans against that roof. So half of that weight, which in this case is half between the roof and the mid-height of the wall, so that's 10 feet, plus the additional 2 feet, that gives us 12 feet, so half of the height plus the parapet. And there's two of those, so we have to calculate both these together. So we're going to look at the weight of all of that. And again, this is looking at seismic shear going from the right to the left. It's cyclic, it will change its direction, and the walls have to go in both directions. So this is going to be just a general purpose building. Call this retail vertical structure. The importance factor is 1.0. So the part that we have to look up, it depends on what the constructive system is. In this case, we're going to call this a light wood frame with bearing walls and shear panels for stability. So in our handouts here, this is from the Uniform Building Code circa 1987. Last time that this particular code was used. We're doing this because it is much more clear than the new codes. The new codes are more accurate, but the older codes are more clear, simpler to understand, and that's our purpose here, is to really understand the behavior. So table 16N gives us this coefficient for the structural system. It's divided up into bearing walls, building frame systems, moment resisting frames, dual systems. Those are combining moment frames with building frames or other types of systems such as a shear wall. And then undefined systems, we're not going to use that. So we're in a bearing wall system, light framed wall with shear panels. We're less than 3 stories. That gives us a RW factor of 8. And don't confuse, that's not RW squared. That's just a footnote down at the bottom here. It says footnote 2, see section 1628.3 for combination structural systems. So it's, our RW factor here is 8. So we'll put that down for calculation. And we are going to do this with 15 pounds per square foot for the roof load, 20 pounds, and 20 pounds per square foot for the wall dead load. So the formula, again, for seismic base shear, given by this formula V, that's the base shear force. So that inertial load is translated into a force that we look at statically in the building. So V is Z times I times C over RW times W. So a certain percentage of our dead load is being factored by this calculation here. The I factor, we've already said that is 1 because this is a non-essential facility. The factor C actually involves a interaction between the building period of vibration and the type of soil that we have constructed on. So C has a lot of stuff embedded into it that I'm not even going to go into, but C is never to exceed, in this code, 2.75. So we'll just use a C factor of 2.75. So that's definitely conservative, and we don't have to worry about that. So right now we're interested in calculating this W right here, the dead loads. So W is this weight of the top portion of the building, the roof, and the 2 side walls. So we have to calculate the dead load in the both north-south and east-west direction. So let's do this in the north-south direction.
So we
have the wall, or roof weight rather. So our roof is 15 pounds per square foot. And our depth is going to be 60 feet. And I'll just set up the calculations right now. Then we have wall, that's 20 pounds per square foot. Our height again is 12 feet because it's half of the height plus the 2 feet of the parapet. And there are 2 walls. Okay, so we have 15 pounds per square foot times 60 feet. That gives us 900 pounds per foot. One of these feet are going to cancel out. So the per foot part, again, is the 1 foot wide strip that exists all the way along here. So that's 900 pounds of dead load from the roof, 60 feet long, every 1 foot of length of the 100-foot building. And then we have the per square foot wall, 12 feet tall. 2 of those walls, that's 480 pounds per foot. Again, feet are going to cancel. So for a total of 1,380 pounds per foot in the north-south direction. So now let's go to the east-west direction. So same type of calculation. We're looking at the roof, 15 pounds per square foot. And this time it's not 60 feet because it's going east-west. It's going to be 100 feet. And then the walls, this is exactly the same as in the north-south direction, because the walls are the same all the way around. So that's 480 for that. So we have our 15 pounds per square foot times 100 feet, 1,500 pounds per foot. Plus our 480, 1,980 pounds per foot. So these then are the dead loads that we are looking at that get activated in this seismic situation. So the magnitude of the seismic force depends greatly on the location that you're positioned at. So here we have our old UBC seismic app. This is from 1997. I think I said 87 previously, 1997 code. And it just very generally maps out regions of the country with varying seismic action. The new code maps look very similar, except they're very dense, very, very precise, and they actually deal with accelerations. This is just a multiplication factor. So it's actually a rather crude technique, but it's actually useful for us. So we're going to be here in Las Vegas. We see this is a 2B. So 2B is a seismic Z factor of 0.2. So we put that into our calculation here. So in the north-south direction, okay, the seismic force in the north-south direction, our zone, that's 2b. That means our z factor, once again, is 0.2. So that's our first term. 0.2 times 1.0 for the importance factor, 2.75 for the C factor. Divide this by 8 for the RW, and that gets multiplied by W. And this is actually, doesn't matter if this is north, south, or east or west. So let's get our multiplication here. 0.2 times 1, obviously that's 0.2, 2.75, divide that by 8. That says 0.7. Let's take that to 3 decimal places, 0.69. About 6.9% of the weight is activated seismically. So let's multiply that out. 0.069 times, this is north-south direction again, 0.69 times 1,380 pounds per foot. So that 0.69 is simply a multiplication factor. There's no units to that. Multiply that by 1,380, and we have 95.22. So we'll call this about 95 pounds per foot. Now we go in the east-west direction. Now we have the same 0.069, but our load is different. Now it's 1,980 pounds per foot. So multiplication factor times 1980 comes out to 136.1. Just call that 136 pounds per foot. So what that means is this 136 pounds per foot in east-west direction and 95 pounds per foot, that's going to be going on to our roof structure here. So that becomes a concentrated force along the top edge. And again, that goes back to the previous 3D model that we looked at with the linear load at the top of the roof. And if there were multi-story, that would be from floor to floor as well. So here's our roof structure. And so in one direction, here's our linear load per foot. In this direction, north-south, again, north is up. This is 95 pounds per foot. In the east-west direction, this is our 136 pounds per foot. So one difference from seismic load and wind load is that with seismic load you'll have two different values for the lateral force because there is more structure in the long direction than there is in the short direction. Wind load will be the same in both directions because you have the same wall faces that were considered. Action of the lateral forces is, if we have a flexible diaphragm, is to cause that diaphragm to bend. So this is a wood structure. We'll consider this to be flexible. And so that pressure is causing the diaphragm to bend in the way that a beam bends. So we get compression on the front side, and tension on the back side. So tension back here and compression up here. And the same thing is true in east-west direction. Although the force is higher, the distance is shorter. So the last thing we want to look at here is what are the diaphragm forces that happen here. Particularly we're interested in this tension force. There's other stuff. There's a shear force that goes through the diaphragm, but we won't calculate in this example. So diaphragm forces diaphragm forces are computed by the moment divided by the distance between the elements. So this is basically a couple between these two forces here. We have tension acting on this side, compression acting on this side, and then the distance between these here. This is going to equal the moment that we generate. And so the moment is like a simple span beam. Here's a beam with a load, causes it to deflect, and we know for a simple span the moment is WL squared over 8. And the deeper the beam is, the lower those forces are going to be. So to expand our calculation here, this is WL squared over 8 times D, where the D is in the same direction that the force is going. So in the north-south direction, that's going to be 95 pounds per foot times our span of 100 feet. Square that, divide that by 8, and the depth of 60 feet. And you can see how this is working out to a force. We have feet squared on the bottom, feet squared on the top, so both of those are going to cancel. So let's multiply this out. That's 95 pounds per foot. (100 feet squared times 95 divided by 8 divided by 60 comes out to 1,979 pounds per foot plus some change. So we'll call that about 1,980 pounds. That's not pounds per foot, that's just pounds. Sorry about that. So that's the tension force that we need to design for on the back side here. So any lap, splices, any kind of connections we have to provide for about 2,000 pounds. In the east-west direction, we have the same calculation but different forces and different distances. So it's 136 pounds per foot times our span of 60 feet, not 100 feet, 60 feet because it's going this way. Square that, divide that by 8, and our D is now 100 feet because the surfaces we're interested in are this one and this one. So let's multiply this out. 136, 60, divide that by 8, and divide that by 100. Gives us 612 pounds per foot. Not pounds per foot, just pounds. Total force pounds. So about 600 pounds. So much lower forces, even though the force is higher in this calculation, because the span is shorter and the depth is deeper, the force comes out much lower. So if you design for 1980 in this direction and 600 in that direction. That would solve for our diaphragm forces. Now the total shear force, the total reaction force, the 95 pounds per foot over 100 feet, divide that by 2, that becomes a reaction here that we designed for. So let's just calculate those forces. So these are loads to the vertical lateral system. So this would be our shear wall or braced frame or rigid frame. It's simply the total load times the span over 2. Now don't confuse this. We'll call this R. Sometimes that's V, but then you confuse that with the seismic base shear. So the reaction is the 95 pounds per foot times 100 feet, and all of that over 2. So that's the same thing as 95 times 50. So 4,750 pounds is the total force at the top of the wall. So that is here. That's our value. R equals 4,750 pounds. This is in the north-south direction. And that's basically how we do the step-by-step calculations. We do the same calculation for the 136. I guess we can go ahead and do that. East-west is 136 pounds per foot times 60 feet, and all of that divided by 2. So that's 136 times 30, 60 over 2. It is 4,080 pounds. That's the reaction force. And these two forces, the 4,750 and 4,080, that is what goes to our supporting shear wall or braced frame or rigid frame. And that's pretty much it, step by step, through the basic calculations for a seismic load.